Okay, so good morning. So in the last class, we had started with POS tagging, right? And we said we will be looking at two different methods for POS tagging. One is rule-based method, which we have already seen, and the second one is a probability-based method. Okay, so in probability-based method, we'll be looking at a specific type of probability-based POS tagging method called HMM-based POS tagging. HMM stands for Hidden Markov Model-based POS tagging. Okay, so basically, the part of speech tagging, it actually is treated as a sequence classification task. Okay, so given a sequence of words, the input is a sequence of words. So we need to generate a sequence of part of speech tags. For example, if you're given a sentence like this, secretariat is expected to raise tomorrow. Okay, so this is a sentence. So corresponding to each one of the word, we have to generate a part of speech tag. Okay, so how do we do that? So basically, what can be done is in a Bayesian inference or in probability-based technique, what we can do is we can start by considering all possible sequence of classes or tags. So given a sentence like this, okay, one possibility, which is we can think of it as a brute force approach, is to list out all possible tags. Okay, all possible tags. Say this first word, secretariat. If you look at it from a human perspective, we know it is actually a proper noun. Uh, but it could also mean it could be a noun, or it could be any tag can be used. So what are the possible tags? Okay, so in probability we say set of all possible combinations, right? So we are looking at all possible sequence of classes, and for each of these we'll estimate the probability of it. Okay, so out of these, we need to decide the most probable tag sequence given the observation sequence of words. So the word is the input W1 raised to N, which means you have a set of words W1, W2, etc. up to Wn. And corresponding to each word, a tag has to be generated. Okay, so that is out of all n tag sequence T1 raised to n, we need to find the single tag sequence which has the highest probability of occurring. Now, how do we get the probability? Because we might have a corpus with us, and from that we will be able to estimate the probability of occurrence of a particular word sequence, and from that we'll be able to get the tag sequence. Okay, so in equation form, you can say, so T1 cap raised to n. It is the tag sequence with the highest probability. So it can be written as R max probability of T1 raised to n. What is the probability of this particular tag sequence given the word sequence? It is found for all the T1 raised to n possible tag sequences, and highest probability all other we will identify. Okay, so this is the computation which we need to do. Now we look at how we are going to do the computation. Okay, now this if you look at this probability, so we know this t1 raised to n means you have tags t1, t2, etc. up to tn. Okay, so which means you have a sequence of tags of size n, where n can be of any length depending on the sentence length. Now, if you look at calculating probabilities of this or conditional probabilities with involving such long sequences of sequences of words or sequences of tags is actually very complicated. So what we do is we will go for some sort of simplification of calculation. Okay, now for that, first of all, we'll use Bayes theorem in order to rewrite the equation which we have seen here. This equation 1 is going to be rewritten based on Bayes theorem. Now, what is Bayes theorem? Bayes theorem states like this: probability of some x given y, conditional probability like this, is equal to probability of y given x into probability of x by probability of y. Now, if you look at an example, we'll explain this Bayes theorem using an example. Let us say we have a basket full of apples and say let us say mangoes. Okay. And we that is a human can actually look at these apples and mangoes and actually easily differentiate between the two. Now suppose a machine is actually looking at it, or using some sensor or some data collected. Based on that, it is trying to classify the apples and mangoes. Now how can it do it? Maybe the parameters which can be taken are the color of the fruit, the shape of the fruit, or the texture of the fruit. Different features can be extracted and given to the machine in order to do the classification, let us say. So that is our problem. So we can that problem can be formulated using Bayes theorem as probability of the fruit belonging to the class apples. What is the probability of fruit belonging to the class apples? Given that, on the condition that fruit has a color of red, and its texture is shiny, and its shape is round. Let us say these are the features which we are talking about. Okay, so what is the probability that the fruit is apple, given that the properties? Okay, that it is red in color is red, it is texture is shiny, and uh, shape is round. Okay, so if you want to calculate that probability, then that is equal to probability of y given x. Y given x means here y, what we said, is the features. So probability of a fruit being red and round and shiny, given that it is an apple. Okay, given that it belongs to the class apple, into probability of x. X here is the class, right? Probability of apples within your data set, divided by probability of red, round, and shiny fruits within your data. Okay, so if you look at it that way, we can say that probability here we are trying to find out, given a fruit, whether it is an apple or a mango, given its properties. That is, it is red, it is round, and it is shiny. Okay, so how do you do that? So if you have lots of apples, that is, if you are in a market, you have lots of apples and oranges. From that, you can estimate the probability of that the fruit being, there is a probability that given it is an apple, that is probability that is an apple, then what is the probability that it is an apple, then what is the probability that it is red, round, and shiny? Okay, that can be calculated. അല്ലേ, ഇപ്പൊ നമുക്ക് കുറെ ആപ്പിൾസ് ആൻഡ് മാംഗോസ് നമുക്ക് മാർക്കറ്റിലുണ്ട്. ദറ്റ് ഈസ് വി ഹാവ് ലോട്ട്സ് ഓഫ് ഡേറ്റ അവൈലബിൾ അബൌട്ട് ഡിഫറെന്റ് ഫ്രൂട്ട്സ്. അപ്പൊ അതിൽ നിന്ന് ഗിവൺ ഇപ്പൊ 100 ആപ്പിൾസ് ഉണ്ടെങ്കിൽ, then you can actually estimate from those 100 apples, you can estimate how many of them out of the 100 apples, how many of them are actually round, how many of them are red, and how many of them are shiny. Okay, that is can be calculated. So this thing can be actually calculated from the data set. Okay, now similarly, probability of x. Probability of x is the probability of it being an apple. Okay, so probability of x means out of the data which you have, or in the market you have got lots of fruits. So what is the probability that you have apples in your data? But you have 2000 fruits, 1000 of them are apples, which means you have a probability of 1 by 2. So that also, this value also can be estimated from the data. And similarly, probability of y. Y is the probability of some fruit being red, round, and shiny, or in the case of mangoes, it is say green, uh, what texture is maybe rough, and it is a shape is not round. Okay, let us say that is how. So these values, what the idea of incorporating Bayes theorem here is, in order to estimate probability of x given y, you can actually each of these values can actually be computed from your data set. If you have data about, say, fruits, then you can compute each of them from the data set. So that is the significance of Bayes theorem. So you can apply Bayes theorem to this particular formula. Okay, here probability of T1 raised to n given W1 raised to n. Okay, so you can rewrite it based on Bayes theorem. Bayes theorem വെച്ച് നമ്മൾ എഴുതുമ്പോൾ you can write it as probability of T1 given W1 can be written as, according to this equation, you write W1 raised to n given T1 raised to n into probability of T1 raised to n divided by probability of W1 raised to n. So Bayes theorem apply ചെയ്യുമ്പോൾ നമ്മളെ equation 1 becomes like this. Okay. Now, what did we say earlier? Basically, we want to find out the tags for a particular sentence or a set of words. അപ്പോൾ അതെങ്ങനെ കണ്ടുപിടിക്കുക എന്നാ പറഞ്ഞത്? We said that you will find all possible tags, all possible combinations of tags. Okay, എന്നിട്ട് അതിൽ ഏറ്റവും highest probability ഉള്ളതാണ് നമ്മൾ കണ്ടുപിടിക്കുന്നത്. Okay, let us say we are talking about the first set of tags, some T1, T2, etc. Tn. അതിന് corresponding ആയിട്ട് നമ്മൾ ഇവിടെ ഒരു value കണ്ടുപിടിച്ചു. Okay, ഇനി second set of tags ആയാലും again you apply this. പക്ഷേ ഇവിടെ you will have to understand the words do not change, only the tags change. Okay, in the calculation. അപ്പോൾ what is significant about this is, since only the tags change for each of the combination of tags, okay, this part, the denominator part, does not change. So you don't have to compute it repeatedly. Okay, so that is how the equation 1 now can be reduced to this form. That is, a denominator namukku eduthu kalayan pattum. Okay, so which means our estimation of tag can be written as like this. Okay, so it is probability of W1 raised to n given tags T1 raised to n into probability of T1 raised to n. Okay, so this is how we are going to estimate. Now, this is also not easy to compute. So what do we do now? Okay, now probability of W1 raised to n given T1 raised to n. Okay, so you have a sequence of probabilities. Now, this is actually conditional probability, right? Now, if in case of conditional probability, if two conditions we are saying are independent of each other, if you have, that is, if you are, the first assumption is that the probability of word appearing is dependent only on its own part of speech tag and it is independent of other words around it. Okay, which means what we are trying to say is, instead of taking a sequence of conditions, when you have studied probability, you must have studied that if you have two independent events, okay, when you have two independent events, in order to calculate the probability of those two events happening, you actually multiply those probabilities. Okay, independent events ആണെങ്കിലാണ് നമ്മൾ അത് ചെയ്യുന്നത്. അപ്പോൾ ഇവിടെ the assumption is that the probability of a word appearing is dependent only on its own part of speech tag and it is independent of the other words. അപ്പോൾ independent condition വരുമ്പോൾ what you do is, this can be actually written as a pi of, അതായത് you are multiplying the sequence. Okay, ഇപ്പോൾ ഇൻഡിപെൻഡന്റ് ഇവന്റ്സ് വരുമ്പോൾ നമ്മൾ മൾട്ടിപ്ലൈ ചെയ്യുമെന്നാണ് പറഞ്ഞത്. So instead of taking this can actually be approximated like this. That is, probability of W1 given T1 into probability of W2 given T2 into probability of W3 given T3, etc. into probability of Wn given Tn. So you can estimate, or you can actually approximate, not estimate, approximate this particular probability as a product of many probabilities, which will be easier to compute for us. Okay, next assumption is now calculation of probability of T1 raised to n. Okay, now how can you do that? It can also be estimated based on the assumption of the Markovian property. When we talked about Markovian, or when we basically Markovian property is like this. uh, the probability of, or the state in which a system will be currently at this point in time will depend only on its previous state and not on anything before. Or we can state it otherwise. You can say that the probability that uh, a system is in state say t plus 1 or next point in time depends only on the state in which the machine is in the current state. So if you take that, that is a Markovian property, and if you take that property into consideration, then you can say, look, probability of an event Ti depends only on Ti minus 1, and it does not depend on any of the previous probabilities. So you can say probability of T1 raised to n can be approximated as a product of these probabilities. That is, T1 raised to n can be written as, you can say, probability of T1 given T0 into probability of T2 given T1, and so etc. Okay, so equation 1, which is like this, can be approximated this way. That is, these two products can be combined to form like this. Okay.